Hi, Eventual Consistency in Logistics. This is my original title, but on the agenda, I only had one question mark, but originally I had five question marks. These five question marks, we'll get into them a bit later, but for now, my original title had five question marks. My name is Lennart Querter. I'm a staff engineer at Forto. Forto is a digital freight forwarder. What does a freight forwarder do? We organize transport for other companies. We coordinate with partners and carriers to ensure on-time delivery of goods and products. And as a digital freight forwarder, we try to give visibility on the process to our customers with digital tools. That's why it's called a digital freight forwarder. The general process of delivering goods is it comes from a warehouse, it goes to a port of origin, we put that on a vessel, the vessel goes to the destination port, and it ends up in a warehouse. That is our general global logistics process. Now, let's talk for 2 minutes about eventual consistency. This is a simple diagram which talks about eventual consistency in a database. We have an application that writes to a database, and at some point in time, pretty quickly in this milliseconds, nanosecond range, it will propagate the changes to other nodes within that database, that when the application reads from the read node, it will get a consistent data. Now, I don't want to talk about databases. I actually want to talk about services. If we look at this diagram, we have an application A that emits an event to application B, which does some logic and emits, again, events to application C and D. And at the end, we have an application X that wants to read the data from C and D together. When we talk about eventual consistency within distributed systems, we talk about the distributed transaction between application A and C and D, and ensuring that that part goes well. Now, let's talk about how this looks in a logistics company, right? We have a vessel that updates the estimated time of arrival, where we have to calculate the container pickup when that estimated time of arrival comes in. Every time we recalculate that container pickup time, we have to replan that transport. We have to update the delivery time, and we have to actually inform the customer. The problem here is that this is one big distributed transaction, because every part of the system does one specific thing. Every service will emit another event where another service has to actually do something with that event and set that data in the database. Let's talk about that eventual consistency stuff, and let's talk about something we in our company call the asynchronous tenants. We have four tenants that I will go into detail about, and I want to start with the four as a general overview. We have the first one as replayability as an obligation for every sender. We have guaranteed idempotency for all consumed messages, and a clear separation of event types. And the last one is we need to ensure some kind of schema ownership for each event type. Replayability, number one. What we mean with this is that a producer can resend all its events over the last hours, days, or weeks. This is kind of like an operational solution for system failures or outages, and it heavily relies on idempotency of messages. If you look at the concepts I explained earlier, where we update the ETA, we recalculate, replan, sometimes something goes wrong. For example, in the replanning of a transport, we get an issue, and that means that we actually cannot update the delivery time. We cannot inform the customer. Where replayability comes in is that we should have an easy way that we can just replay the event of calculating the container pickup time, and the replanning of the transport can proceed. There are some patterns that kind of help us solve this problem, one of them being an outbox pattern. This is how a general service would kind of look. You consume a message, you do some logic, you store that the result of that logic in a database, and you emit an event. If every time we emit an event, we can actually choose to store that also into an event database and have some kind of functionality to pick up those events and just replay them directly back into the topic. This is a very easy implementation of the outbox pattern, which will help you easily achieve the first tenet, which is replayability. I talked a bit about item potency, and one of the things that we also want to ensure is that every message is item potent. This means that when we re-emit the events, which we do quite often because of the replayability concept, there is no harm when we consume these messages. The messages, they all have to contain a unique identifier so that the consumer can kind of decide how to handle these events coming in. They can ignore outdated messages. Let's say they have an event, their internal representation of the domain model is newer than the event that we just pushed, then they can just ignore it. They can keep track of what messages that have been consumed by that unique identifier that we just talked about. They need to be able to reprocess the data every single time. So every time the messages that come in, they need to reapply every change every single time. The most important thing is that the implementation of how to handle these events are private to the consumer, meaning that only the consumer knows how it handles the incoming events. Going into the third tenets, we talk about event types. We want a clear separation of event types, right? We want our events to always look the same way. For example, a producer publishes to a topic, which then gets pushed to different queues. This is kind of the fan out method, right? Every queue has a consumer linked to it, and there can be multiple consumers, of course, based on your load and your scalability. And the second type of event is we have commands where we kind of skip the topic and we have a producer A that directly pushes a command into a queue for a consumer. Let's talk a bit about schema ownership, which is our fourth tenet. We want schemas to be owned by different types of services. For example, if we're talking about event types, so more the fan out pattern, we want to ensure that the producer owns that schema, so that when other services are consuming the events, that they adhere to the schema defined by the producer. The other way around, when we're talking about commands or kind of collect pattern, we want the consumer to own that schema and provide it to the upstream service that is triggering that command. We also want to ensure that schemas need to be provided in a consistent way, right? We have libraries, specification files. There are a lot of patterns that we can follow to make sure that these schemas are provided. I have two remarks about like FIFO and dead letter queues. They are FIFO first in, first out topics and queues. They are not a requirement if we kind of follow these four tenets, right? Because with replayability and item potency, we kind of figure out that we can replay events whenever we want. So we don't need first in, first out. And the item potency ensures that when we consume duplicated messages, we will always get the exact same results. Also, dead letter queues, they don't become something that you replay often, or you don't redrive them. You actually use them more for alerting and monitoring, meaning if there are messages piling up in your dead letter queues, that means something is going wrong, something that needs to be investigated by one of us as engineers, right? Going into the second part of the problem we have within eventual consistency in logistics is multiple data sources. We talked about this distributed transaction, and following the four tenets could be a way to really ensure that the process completes end to end. The next problem, or the next issue I want to talk about, is like these update ETA events. They come from external systems, meaning that, yeah, can we really trust them? Are we sure that the providers that we're using will send us the correct data? As an example here, I can show you all the different data sources that we kind of use within our transport management system. We have IoT tracking, we have an operation manager, we have direct port integration, carrier integration, and we even use bots that scrape the internet for updates and schedules. All of these events come into our transport management system, and this looks a bit like this. This is a screenshot from what our production environment looks like. It's not the greatest UI, I know, but it does what it should do. If you look on the left column that I marked, these are the estimated times of arrival of a vessel. If you look at the bottom, it goes up, meaning some operation manager set a certain date, and then we have integrations, Ocean Insights, or our data science bots, RPA. We have port bases, our ports integration. And you can see that they're kind of fighting for a certain time of arrival. They are not really sure. If we look back at the process, every time one of these timestamps is updated, we need to change the estimated time of delivery for the customer, meaning that this becomes a problem because we are updating this so many times that we are sending a lot of emails to our customers that don't really make sense. Let's talk about our tracking engine. The way that we kind of try to fix this issue was having a tracking engine. We have all our integrations at the top level, and we have a tracking engine in the middle. And based on some simple kind of rules, we wanted to prevent events from getting through. These are kind of our high level rules that we have. For example, if the estimated timestamp is 10 days different than the previous, we can kind of ignore it. Also the same, if the vessel has actually already departed the port of loading and there's a change by 5 days, we kind of mark it as suspicious. The same with if the port of destination changed, but that new port is already on the route, that's a bit suspicious for us. Then we have new port of destination is on a different continent. That also doesn't really make sense. We also have a bucket of events that kind of are things that we just ignore. Like estimated timestamps are 21 days different than the previous one. We just don't ingest them. If the estimated timestamp is the same as the previous one, we actually also can ignore it, but we can increase the confidence in that timestamp. Now, what we do with these suspicious events is we actually are labeling these events, and we use a cool tool called Slack. We use a kind of chat ops flow to notify the operation manager that's assigned to that shipment that there's a suspicious timestamp coming in. The operation manager can then actually approve or decline that timestamp in Slack, and we label our data. We push it into our tracking engine or not. Now, what we're actually doing is we're labeling data, which in the end will allow us to go into AI or machine learning, well, linear regression. In the end, it's just kind of math, right? So what we do and what we want to do is kind of replace this operation manager manually approving or declining stuff with an automated system that will be able to understand what type of events are coming in, and if we can mark them as suspicious, discard them, or just automatically approve them. This would look something like this. We have our integrations on one side, we have our super accurate machine learning model in the center, and this would approve or mark suspicious or reject a event. If we approve it, we insert it directly into the tracking engine, but if we mark it suspicious, we can reuse the flow we already built, right? The operation manager will still need to approve or decline. And with that information, we can retrain our machine learning model to make it even more accurate. This is kind of how it would look in the end. We have an operation manager setting an estimated time. We have our bot saying, okay, it's the 30th, and actually it arrives on the 30th. Great. Talking about my title, Eventual Consistency in Logistics, 5 question marks. I had 5 questions when I started doing this talk, and the first one was, how can we ensure that distributed transactions are completed? And this is kind of what we're already doing at our company. We have those 4 tenants that we try to follow as closely as possible, so that when failures happen or systems don't behave as we expect, we can always ensure that somehow we can replay events or have the events complete in an idempotent manner. The second one was, how can we minimize the impact of wrong events in our internal system? And that's by preventing or like funneling the input, right? So marking events as suspicious or completely ignoring events means that we get less trash in our system and we have to process less events over the whole flow. How can we train a system to understand which events are good and bad? That's kind of, we do that by letting the operation managers label the data and then crunch the data with a simple machine learning model. This one is better in person, but can I randomly drop the word AI in a conference talk about logistics and eventual consistency? Well, yes, I did. I didn't really put too much emphasis on it, but I feel that in the future this will be a bigger thing, or at least something that we can use to train our models and prevent wrong or suspicious events coming in from our system. And the last question that I'm not really 100% sure of is, are loosely coupled microservices the right fits? Again, here we saw a big distributed system, and I keep wondering, what if it's just one system that handles this whole flow? It might just be easier to manage, to develop, to deploy. I'm not sure. Maybe this is for my next talk. So this was my 4 questions answered, one I'm not 100% sure about. And yeah, that was a bit my talk. Thank you very much for listening. And yeah, hope to see you